Hi Pallavi. Yeah, let's wait for just 2 more minutes since people are joining, then we can start, okay? Okay, I think we will just begin. People are joining, let them. Okay. I'm not sure who all were you, like who all were there in the last class. So if someone new was there, I think I'll just start by introducing myself. So I'm Nandini Ji. I'm currently a PhD scholar at IIT Bhubaneswar, and I have completed my MSc in meteorology and BSc in physics. And currently, I'm working on urban climate. So yeah, so this is my fourth year in PhD. Okay, so that's all about me. I think we'll start then. So last class we were discussing about Sun-Earth relationship, atmosphere, composition of the atmosphere, temperature, variation in the atmosphere, and all those things. So today we will have a look at how the atmosphere evolved. Like we have our present atmosphere, which is basically as we were discussing in the last session, that there is 78 percentage of nitrogen and 21 percentage oxygen in the current atmosphere. So let's have a look at how this atmosphere kind of evolved. So it is believed that it is said that the Earth's first atmosphere, like around 4.6 billion years ago, was most likely composed of hydrogen and helium. So the first atmosphere, which was around 4.6 billion years ago, that is when the Earth was formed. At that time itself, the atmosphere was initial atmosphere, or the first atmosphere of Earth, was abundant in hydrogen and helium, because these two are the most abundant gases found in the universe. And scientists, one of the theory that is widely accepted by the scientists is that this atmosphere, which was present during the formation of the Earth, it escaped into space because the gravitational force of the Earth was not that much strong enough to keep the atmosphere to the Earth. So because of that, this first atmosphere which was found, it kind of escaped into space. So there are different theories, but this is the most accepted theory regarding the first first atmosphere. So this is basically known as the primordial atmosphere, first. And then after some million years ago, after some million years, a second more dense atmosphere found in the Earth. So how this found was basically the gases from the molten rocks in the Earth's interior started to getting emitted through the volcanoes. So like because of the very high temperature in the interior of the Earth, the rocks were getting melted, and the gases emitted due to these molten rock were getting emitted to the atmosphere through the volcanoes. So this emission through the volcanoes was mostly composed of 80% of water vapor, 10% of carbon dioxide, and a few percentage of nitrogen. So after the first primordial atmosphere, which was rich in hydrogen and helium, there formed a secondary atmosphere, which was rich in water vapor and carbon dioxide, 80% of water vapor and 10% of carbon dioxide, which was basically the emissions from the volcanoes. The gases from the molten rock within the hot interior of the earth was being emitted through the volcanoes to the atmosphere. So that was the secondary atmosphere that formed. And this process of volcanic emission continued for several years, several thousands of years. And what happened is that the Earth's second atmosphere became abundant in water vapor. The water vapor content in the atmosphere increased a lot. So because of that, the water vapor started to condense and started to form cloud droplets. And eventually it started to rain. And this rain continued to occur for almost thousands of years. And then this resulted in the formation of rivers, lakes, and oceans of the world. So, when this rain was happening, what happened? So, as I told, it was rich in the secondary atmosphere was basically rich in water vapor and carbon dioxide. So, the water vapor which was present condensed, formed cloud droplets, and eventually caused the rain. What happened to the carbon dioxide? So, the carbon dioxide which was present in the atmosphere started to dissolve in the oceans. As the oceans formed, the carbon dioxide which was in the atmosphere started to dissolve in the ocean. So, a large amount of carbon dioxide was removed from the atmosphere, and a huge amount also, um, because of different chemical and biological process, kind of trapped in the sedimentary rocks which was on the surface of the earth. So the sedimentary, some carbon dioxide also got trapped in the earth's surface due to different biological and chemical process, and that's what like seen as limestones and all. Like it was trapped in carbonate sedimentary rocks such as limestone. So that's how carbon dioxide was removed from the atmosphere. So the because of the abundance of water vapor, it started to rain, and while it was raining, the oceans, rivers, and lakes formed, and then the carbon dioxide, which was present in the atmosphere, started dissolving in the ocean, and a large amount was removed from the atmosphere, and also a few amount of carbon dioxide also was trapped in carbonate sedimentary rocks like limestone. So the secondary atmosphere started to change. So as the amount of water vapor and carbon dioxide started to decline in the atmosphere, it slowly started to become enriched in nitrogen. So the another component which was present in very small quantities in the secondary atmosphere, which was nitrogen, started to become uh, more abundant as the water vapor and carbon dioxide started to decline in the atmosphere. So now we have nitrogen started to become abundant, and then as this transformation from secondary atmosphere which is absent in oxygen, as we can see this doesn't have an oxygen, so it started evolving. How did it evolve to the present atmosphere which is having 21% of oxygen? How did oxygen come to the atmosphere? So as the water vapor, these things were happening, the oxygen started to slowly increase in the atmosphere due to a process called photodissociation, which is basically the incoming sun's rays started to split the water vapor molecule. So there is water vapor in the atmosphere. So the incoming radiation or solar rays started to split the water vapor molecules into two. That is hydrogen and oxygen. The hydrogen molecules, which is a very lighter molecule, which is a very less mass, it started to escape from the atmosphere. It escaped from the atmosphere, and finally only oxygen remained in the atmosphere. So this was the method through which oxygen first came in the atmosphere, and this formation of oxygen was a very slow process. So the amount of oxygen formed due to photodissociation was very less. Then what happened, as the oxygen started increasing in the atmosphere, slowly the plants very like um, the plants which needed very less amount of oxygen started to form in the earth, and also those plants which can survive in an anaerobic environment, that which doesn't need oxygen, also started to form in the earth. So as plants started growing or plants started evolving, what happened is that through the process of photosynthesis, these plants started emitting oxygen to the atmosphere, which eventually led to a rapid increase in the composition or in the amount of oxygen atmosphere present in the atmosphere. So that's how the atmosphere reached in its current form with 78% nitrogen and 21% oxygen. Okay, so what was it? So first atmosphere, which was formed around 4.6 billion years ago, was known as a primordial atmosphere. It was rich in hydrogen and helium, and this was like most of the scientists agree with the theory that this atmosphere escaped from the Earth's surface because the gravitational pull of the Earth was not very stronger at that time. So that was the primordial atmosphere. Then we had a secondary atmosphere. So secondary atmosphere was rich in water vapor, carbon dioxide, and a few percentage of nitrogen. So this was formed by the volcanic emission. So what happened is that the gases from molten rock in the Earth's hot interior escape through the process is basically known as outgassing. So the gases from the interior of the Earth is being emitted to the atmosphere through volcanoes. So this process was known as outgassing. So through the process of outgassing, the water vapor content in the atmosphere started to increase, and as a result, clouds were started forming, and it eventually resulted in rain. So this rain continued to persist for almost thousands of years, which basically resulted in the formation of oceans, lakes, and rivers. So as this rain was happening, the carbon dioxide which was present in the atmosphere started to dissolve in the ocean, and some were trapped in carbonate sedimentary rocks such as limestone. So that's how secondary atmosphere slowly started to change. So the water vapor was being rained out and carbon dioxide was being dissolved in the ocean. So whatever nitrogen, the atmosphere slowly started being enriched in nitrogen. And then how the oxygen came into the atmosphere is through a process known as photodissociation, which is basically the sun's rays is splitting the water vapor molecule present in the atmosphere into two, hydrogen and oxygen. So the hydrogen, which is a lighter molecule, is escaping from the Earth's atmosphere, and oxygen was staying back in the atmosphere. So initially, this was a slow process actually, and this was a process by which oxygen started to increase in the atmosphere. And as the oxygen started to increase slowly, plants started to evolve, and those plants which doesn't need oxygen to survive, which can survive in an anaerobic environment, started to evolve. So as the plants started evolving through the process of photosynthesis, they started emitting a large amount of oxygen. So this was a rapid process, or like then the oxygen concentration in the atmosphere increased rapidly, and finally it reached the current condition or the current composition of the atmosphere, which is basically 78% nitrogen and 21% oxygen. So this happened around 100 million years ago. So this atmosphere, which is in the present form, was basically formed around several hundred million years ago. So that's how we reached in the present atmosphere. So this is just a basic idea about how the Earth's atmosphere kind of evolved. Now let's look at an interesting fact. So suppose consider that the Earth's atmosphere Earth doesn't have an atmosphere. So then we can try to calculate the Earth's temperature. So suppose if Earth was not having an atmosphere, what would be the temperature of the Earth? So that's what we are trying to calculate. So we have to calculate the temperature of the Earth. So how can we calculate it? So as we last class we were talking about, we learned a lot of we learned different radiation laws and all. So suppose if we know if we know the amount of radiation, we were talking about black body, how a body which is at a temperature greater than absolute zero is emitting radiation. And suppose if we know the uh, temperature of a body, how can we calculate the energy being emitted, all these things we were discussing. And we talked about Stephen Boltzmann law, which basically tells if a body is having a temperature T, the energy emitted, what will be the energy emitted by the body. So anyone remember what was Stephen Boltzmann law? The equation basically. Stephen Boltzmann law. Does anyone remember? Anyone? Yeah, thank you. So Stephen Boltzmann law is basically given as E is equal to sigma T raised to 4. So E is the energy emitted by the surface and T is the temperature of the surface. So what we want to calculate is the temperature of Earth. So we want to calculate T. So what we should know? We should know what is E. So first we will find how we will see how can we calculate this the value of E. So last class we also studied about solar constant, which is basically the amount of radiation or amount of energy reaching the top of the atmosphere of the earth per unit area. So we calculated the value of solar constant. Does anyone remember the value? What was the value of solar constant? We calculated it using Stephen Boltzmann law. What was the value of S? Yeah, 1398. Yeah, thanks. So it's basically, so that one was we calculated the value after some assumptions. So generally it is said to be 1370 watt per meter square. So this is the value of solar constant. So solar constant is basically the amount of energy that is reaching the top of the atmosphere per unit area. So since we don't have the atmosphere, we can consider that this value like 1370 watt per meter square is reaching the surface of the earth. So as I said, this is the amount of energy reaching here, surface of the earth. Just 1 minute. Just a sec. क्या हुआ दीदी? Can I talk to you for a while? No, no, actually I'm in a class. Can you please? Yeah, sorry. See. So this amount of energy is basically the amount of energy reaching the, since we don't have an atmosphere, we can consider this much energy is reaching the surface of the earth. So as I said, this is basically per unit area, amount of energy reaching the surface of the earth per unit area is given by solar constant. Now we are going to calculate the total amount of energy that is reaching the surface of the earth. So as we know, like the one if one side of the earth is facing the sun, the other side will always be dark. So the sun's rays are illuminating only one part of the earth. The other side, which is opposite to the sun, which will be basically dark. So when we tell like if this much amount of energy is reaching per unit area, and we want to calculate the total amount. So what we will do is we will multiply this 1370 into pi r e square. So why pi r e square is because this solar radiation is illuminating only one part of the earth, not the earth as a whole. One part will always be dark and only one part is being illuminated. So if we extend this part which is being illuminated or which is basically dark, the area is it is kind of it kind of extrapolates into a disk. So the area of the disk is basically pi r e square. So if we want to calculate the total energy reaching the surface of the earth, it will be into pi r e square, which that is the area that is being illuminated by the sun. So that is S. So this much amount of energy is reaching the Earth's surface. S is equal to 1370 into pi r e square. R is the radius of the Earth. Now, so this much energy is receiving. Suppose let us assume whatever energy is coming is absorbed by the Earth, and what will be S. Okay. So this much energy is coming to the Earth. So let us calculate how much will be re-emitted by the Earth. And as I told, the absorption is basically only to the illuminated surface. But when we are considering the emission, it will be from all parts of the Earth. That is as seen in this red arrow. The incoming radiation is only illuminating this part. After absorbing this much of radiation, Earth will start re-emitting the radiation. So as the Earth is re-emitting the radiation, it is going in all sides of the Earth. It will go on all sides, not only this side. So if we want to calculate the energy emitted basically, so this is the energy absorbed by Earth. Now if we want to calculate the energy emitted, it will be 1370 into pi r e square by 4 pi r e square. So 4 pi r is, this is per unit area, energy emitted per unit area by Earth. So this is the energy being absorbed and divided by the total area over which the energy is being re-emitted. So that is basically the area of the Earth, that is 4 pi r square, area of the sphere basically. So it will be 1370 into pi r e square by 4 pi r e square. This is the energy being emitted by the Earth. Assuming that whatever be the radiation that is coming, the Earth is absorbing the whole energy. So this is the energy absorbed and it is being re-emitted. So this will be basically S by 4. 1370. Okay, well, let's not call it S. We will call it E. Because we call it S, it will be confusing. S is basically solar constant, right? Yeah. So let's call this E, energy emitted. So this will basically, this is S, pi r e square. Pi r e square, if we remove it, it will be S by 4. So the energy being emitted by the Earth is S by 4. How much it will be? Can you tell me? Okay. Yeah. 342.5 watt per meter square. So what we did, what is our objective? Our objective is to find the temperature of the Earth. Okay. So for that we use the Stefan-Boltzmann law, which says basically E is equal to sigma T raised to 4, where E is the energy emitted by the surface and T is the temperature of the surface. So we have to calculate T. So for that we should know what is the energy emitted by Earth. That is basically E. So we initially try to calculate E. So to calculate E, what we know how much energy is being received at the Earth. We calculated it using the solar constant. So solar constant is basically the energy received per unit area of the Earth. So per unit area, this much an amount of energy is being received. Now we want to calculate what is the total energy that is received at the surface of the Earth. So in order to calculate the total energy, we multiplied it with pi r square, the disk, the area of the disk. Why we calculated the area of the disk? Because the sun is only illuminating one part of the Earth while the other part is always in the dark. So only pi r square area, that much area is only receiving the solar radiation. So the total energy absorbed will be 1370 into pi r square. So this is the energy absorbed. Now we want to know. So in the Stefan-Boltzmann law, this is basically the energy emitted, right? It is not the energy. The energy is basically the energy emitted. So now we know this much energy is absorbed. So after absorbing this much energy, Earth will start re-radiating the energy. So while re-radiating it, it is being emitted from all directions. So we divide the total energy absorbed by 4 pi r square, total area of the earth. Then we will get S energy emitted is equal to S by 4, which is equal to 342.5 watt per meter square. So this is the energy emitted. So now in this case we assume that there is no atmosphere and there is no other loss of energy, right? That is whatever is being emitted from the sun and whatever is being received by the earth. The earth is absorbing the whole energy and after that it is re-emitting it. That's what we consider. So even though if there is no atmosphere, there is another way in which we are losing some of the energy being received at the earth. So what is it is basically known as the albedo. So albedo is basically the percent of radiation returning from a given surface compared to the amount of radiation initially striking the surface. Suppose this is Earth. We have incoming solar radiation. So what we assume now, we assume that whatever radiation is coming, Earth is absorbing the whole and it is re-emitting it. That's what we have considered now. But actually what is happening is after reaching the Earth's surface, before the Earth's surface absorbs the incoming solar radiation, some amount of it is being reflected back. So some amount of energy of the incoming solar radiation is being reflected back to the atmosphere. So the amount that is reflected back is known as the albedo. Like how much percentage of radiation is being reflected back to the space is known as the albedo of the surface. So it is basically expressed in percentage. So if we consider Earth's surface, in Earth's surface we have multiple surfaces like snow. We have snow coverage over some regions. Then in the atmosphere we have clouds. Both thick clouds are there, thin clouds is there. Then ice sheets are there in the atmosphere. Sorry, ice sheets are there in the Earth's surface. Some part is covered by ice sheets. Then we have sand over some places. Then like vegetation is there. So we have and forest is there. So we have different type of uh, land surfaces over the earth: snow coverage, clouds, ice, sand, etc. So each of these surfaces has a particular albedo for them. So suppose the incoming solar radiation is reaching a region or is over a region with fresh snow cover, almost 95% of the incoming solar radiation is being reflected. That is, if 100 watt per meter square is coming, 95 watt per meter square is being reflected and only 5 watt per meter square is being absorbed by the surface. That is the case in case of snow. Now if we are considering clouds, in case of thick clouds, almost 90% of the incoming radiation is being reflected back and only 10% is being absorbed. And in case of thin clouds, it is 50%. And when we consider ocean and land, like water and land, in case of land or sand, it is higher, like albedo is comparatively higher, which is 15 to 45%, whereas in case of ocean or water, the reflection is basically less. The albedo is less, it absorbs most of the incoming radiation. So that's in case of water. So as the earth has multiple surfaces like this, considering all these complex surfaces, we have calculated, or there is a constant, there is a value that have been calculated as the albedo of the earth as a whole. Not considering individual surfaces, but considering as a whole, this is the albedo of the earth. That is 30%, or if we zero, if we consider one as the maximum, one as the maximum value and 0 as the minimum, it is basically 0.3 is the albedo. So 1 means basically totally it is being reflected back and 0 means a whole of it is absorbed. So it is 0.3, it comes in 0.3. 0.3 is the albedo of the earth. So what it basically means that out of the incoming solar radiation, before the earth is absorbing the radiation, 30% is being reflected back. So now what we assume to do the calculation is that whatever is coming to the earth, whatever with incoming solar radiation, the earth is absorbing the whole and then re-emitting it. That's what we assume. So we calculated E absorption and E emission. Now what we just found is that the whole some of the incoming radiation is being reflected back before the earth is absorbing it. So we have to we have to consider this quantity also. So now we have E absorption, which was yeah. So we have E absorption as 1370 into pi r e square, right? So from this we have to account for albedo also. So into 1 minus alpha. Out of the coming radiation, out of the coming amount, that is 1370, total amount received is 1370 into pi r e square. Out of this, 30% is being emitted. So only the remaining, that is 70% is being absorbed by the earth. So that is accounted by 1 minus alpha, where alpha is the albedo of the earth, which is 0.3. So 1 minus alpha, only this much amount is being absorbed. So that's how we account for E absorption. Now E absorption has changed. So E emission will be, so this is basically S by 4 into 1 minus alpha. So this is the energy emitted by the surface of the earth. S by 4 into 1 minus alpha. Now we have E. So this E we have found, right? Now we have this E. We have found this E, which is basically S by 4 into 1 minus alpha. Now we can calculate T. Now we can calculate this T value. So what we did, we were trying to calculate the energy emitted. Sorry, we were trying to calculate the temperature of the earth. So for that we are using the Stefan Boltzmann law, which is given by E is equal to sigma T raised to 4. So in order to calculate T, we should know what is E. So E is basically the energy emitted by the surface. So what we know is basically the amount of radiation that is reaching the Earth's surface, which is 1370 watt per meter square. So this is basically per unit area. So in order to calculate the total energy that is being absorbed, we multiplied it with pi r e square. This is the area of the disk that is being illuminated by the sun's rays. So that is 1370 into pi r e square. So this is the energy absorbed. So what happens is that this much amount is coming to the surface of the earth, and out of this alpha amount is being reflected back. So we are only getting 1 minus alpha of 1370 into pi r e square. So then we changed the E absorption into, after considering albedo, it was multiplied by 1 minus alpha, where alpha is equal to 0.3 albedo of the earth. So now we have E emission is equal to S by 4 into 1 minus alpha. So with this we can calculate T, right? So so energy emitted is equal to S by 4 into 1 minus alpha, where S is equal to 1370 and alpha is equal to 0.3. Can you please try to calculate E? What will be E? Please calculate that. Oh, 239 it is coming. Did anyone else got the answer? Okay. 239. I think everyone got. So it is basically coming as 239 watts per meter square. So this is the energy emitted by Earth. So E is equal to sigma T raised to 4. So we have to calculate T, right? T is basically fourth power of E by sigma, which will be fourth root. Do you guys remember the value of sigma? Yeah, the value of sigma is 5.67 into 10 raised to minus 8. So can you tell me the value of the temperature of the earth? T will be if anyone got, just post it in the chat box, or you can just say E is basically 239. We just calculated the value of E, this 239, divided by sigma, that's just 5.67 into 10 raised to minus 8. Okay, I guess it is taking a lot of time. You guys calculate it and guys work it out. Okay. The value will come to be around 255 Kelvin. Okay. Anyone got? You just have to divide it and then find the fourth root. Okay, you guys will get it. You just work it out. So this much Kelvin is coming basically. So it is basically 255 minus 273 degrees Celsius, which will be around minus 18 degrees Celsius. Minus 18 degrees Celsius. So this is the temperature of the earth that we got considering there is no atmosphere. Is this the temperature of the earth? Are we living in an earth with a surface temperature of minus 18 degrees Celsius? No. The temperature of the earth is around 20 degrees Celsius or something. So this water additional amount or additional heating that is happening is actually because of the earth's atmosphere. So this, suppose if there was no atmosphere or this greenhouse gases, what would have happened is whatever energy is being re-emitted from the earth, that is this 239 watt per meter square as we did, this much amount is being re-emitted from the earth. But what is happening is that the presence of atmosphere and greenhouse gases, this amount of energy is not leaving the earth's atmosphere. So when the earth is emitting this much amount of energy, the greenhouse gases present in the atmosphere is actually absorbing it and re-emitting it back to the earth. So what happens is that earth remains warmer. So because of the greenhouse gases, the earth is actually warmer than earth is actually warmer and we are able to sustain here. So if there was no atmosphere, the temperature of the earth would have been 255 Kelvin or minus 18 degrees Celsius. I hope the calculations are clear for you. We calculated basically using the Stephen-Boltzmann law, E is equal to sigma T raised to 4. We first found out E, which is basically the energy emitted by the Earth's atmosphere. So we started with solar constant and then we worked it out and then we found the energy being emitted from the Earth's surface. So we also considered the albedo of the Earth, which is basically the amount of energy that is being reflected back to the space before absorption is happening. Before Earth is absorbing any amount of energy, some amount of energy is being emitted back to the space. That value is given by albedo. And as I said, in the Earth's surface, there are different types of surfaces are there. So we have deserts, we have oceans, and we have snow covers, we have ice sheets, we have different kind of surfaces we have. So all these different have their own particular albedo depending on the surface. As I said, in case of snow or ice, the reflectivity or albedo is very much high, that almost zero point 0.9, zero point 0.8 kind of. That is out of the energy reaching these surfaces, almost 90 percentage or 80 percentage is being reflected back. Only 10 percentage is being absorbed. So that is the condition in case of ice sheets, glaciers and all. And if we are considering oceans, as we know, most of the earth's surface is covered by ocean, whereas in case of oceans, the albedo is comparatively less. That is, most of the energy that is coming, the oceans are actually absorbing it instead of re-emitting it back, not re-emitting, instead of reflecting it back to the atmosphere. So oceans have a lower albedo, whereas snow have a higher albedo. And then we have clouds in the atmosphere. So when we are considering clouds, clouds are having an albedo. So in case of clouds are also having a higher albedo. So in case of clouds, for thick clouds the albedo is high and thin clouds it is comparatively less. Thick clouds it is around 0.5 and for thin around it is coming around 0.3 or something. So after considering, and then we have different land surfaces such as deserts, forests and all these things. So all these surfaces have their own characteristic albedo. So generally land surfaces or deserts tend to reflect more rather than absorbing, whereas forest and all tend to absorb more. So considering all these land surfaces, like all these conditions, all these complex terrains of the earth, we have found a constant or a value for the combined value for the albedo of the earth, which is 0.3. So we found if this much is being reflected back, we calculated how much will be absorbed. So which we got as S into pi r e square into 1 minus alpha. And then so this much is being absorbed. And then what is the emitted radiation we calculated? So it is coming as S by 4 into 1 minus alpha. So this is the energy being emitted. So from this we calculated, so the energy emitted was found to be 239 watt per meter square. Now using the Stephen-Boltzmann law, we calculated the temperature of the earth, which is coming to be 255 Kelvin or minus 18 degrees Celsius. So this would have been the temperature of the earth if atmosphere was not present. So the actual temperature is 20 degrees Celsius. So what is happening is that as this much amount of like 239 watt per meter square energy is being emitted by the earth's surface, the greenhouse gases present in the atmosphere absorbs this radiation and then warms the atmosphere or warms the earth's surface. So that's why we are having a higher temperature like 20 degrees Celsius or 283 Kelvin. So that is basically the temperature. So we calculated the temperature of the earth. So what is basically greenhouse effect? Just go through it once more. So as I was talking in the last session, the solar radiation that is coming from the sun is basically short wave radiation. That is, the wavelength is mostly in the visible range. We calculated the lambda max, the wavelength at which maximum emission occurring using Wien's displacement law, again with temperature. So it was lambda is equal to C into T. Lambda max is equal to C into T was the equation. So since we know the temperature of earth and sun, we calculated lambda max. So that was Wien's displacement. So if you guys remember, in case of sun, we got like the maximum radiation, wavelength of maximum radiation was coming in the visible range around, I think we got around 400 or 500 nanometers. So the radiation coming from the sun is considered to be of short wave radiation, like short wave range, incoming short wave radiation. So out of the incoming short wave radiation, the greenhouse gases or the Earth's atmosphere is totally transparent to the incoming short wave radiation from the sun. So as the radiation is coming, the Earth's atmosphere is not absorbing or um, is not absorbing the incoming short wave radiation. It just allows it to pass through it without causing any change. I'm talking about the gas molecules, okay. It has different effects when we are considering aerosols, clouds and all. Now I'm talking only about the gas molecules. So the gas molecules doesn't interact with the incoming solar radiation and it is allowed to pass through the atmosphere. This atmosphere is totally transparent in case of incoming solar radiation. So after reaching the Earth's surface, what happens is that Earth absorbs this radiation. And after absorbing, the Earth will reach a particular temperature and then it starts re-emitting the radiation, which we found to be, again we found the maximum wavelength that was Earth is emitting, and we got it in the infrared range basically. So Earth is re-emitting in the infrared radiation or long wave radiation. So outgoing, this is outgoing long wave radiation. So this is incoming short wave radiation, and what the Earth is emitting is outgoing long wave radiation. So the outgoing long wave radiation that is being emitted by the Earth is being absorbed by the atmospheric greenhouse gases. So the atmospheric greenhouse gases is basically transparent to the incoming solar radiation, whereas it absorbs the outgoing long wave radiation and then it traps the outgoing radiation in the atmosphere and then re-emits it back to the earth. That's how the earth remains warm. Otherwise, it would have been freezing, like minus 18 degrees Celsius would have been the temperature of the earth. So basically greenhouse effect is good, right? That's what we found out. If the greenhouse gases were not there, the Earth's temperature would have been minus 18 degrees Celsius. But since it is there, we are able to survive in Earth. That it is actually having a temperature of 20 degrees Celsius. And so why we are worried about greenhouse effect? It is actually good, right? That's what we learned just now. Do you know why we are actually worried about greenhouse effect then? Is it good or bad? Yeah. So basically, the important greenhouse gases that are in the atmosphere is water vapor, carbon dioxide, and methane. So this is actually good, as he said. Greenhouse gas effect is good, but what happens is that the levels of carbon dioxide and methane are actually going up. So if amount of quantity, it is actually causing an additional warming to the Earth surface. So the Earth is keeping on warming. That is what we call global warming, enhanced greenhouse effect, climate change, all those things. So what is happening is that the amount of carbon dioxide levels is exceeding beyond our control due to anthropogenic emissions, fossil fuel burning, all these things. The amount of carbon dioxide is increasing in an alarming rate. So that's why we are worried about greenhouse gas effect. And water vapor, as I told you in the last class, water vapor and carbon dioxide are the most important greenhouse gas. But we generally talk about carbon dioxide only. We never talk about water vapor. Alarming rate of increase of water vapor are never. What is the thing? So what happens is that in case of water vapor exists in different forms in Earth, like as in water, ice, then vapor. Three different forms: solid, liquid, and gaseous forms. Three different forms it exists. So what happens is that when the amount of water, this amount cannot exceed a particular level because it is always in that cycle. If the water vapor is high, then it will condense into liquid. If it is the temperature is dropping again, it will solidify into ice. So the amount of water vapor present in the atmosphere is always constant. It is not increasing or decreasing. That's why we are not worried about water vapor, even though it is an important greenhouse gas, just like carbon dioxide. Water vapor is the outgoing long wave radiation. So this is also carbon dioxide, just like carbon dioxide. We are not worried because the amount of water vapor in the atmosphere more or less remains constant. It doesn't increase. But in case of carbon dioxide, we are worried because the amount of carbon dioxide is increasing beyond and a required level, or it is increasing very in an alarming rate. So that's why we talk about carbon dioxide and we are worried more about carbon dioxide. And just like this, methane is also another important greenhouse. So that is greenhouse effect. I hope it is clear. Yeah. Okay. So this also we were talking about in the last class. Just for a revision, I am just telling. So basically, if we consider the composition of the atmosphere, it is mostly composed of diatomic nitrogen and oxygen. We learned about that. Almost 78% is nitrogen, 21% is oxygen, and water vapor is there. The third most abundant quantity is argon. It is around 0.93 percentage is argon in the atmosphere. So and then comes water vapor. So in case of water vapor, the value is not a constant. You can see in case of nitrogen it is 78, oxygen 20, argon 0.93. But in case of water vapor, it is written like 0 to 5%. It is not a constant value because the amount of water vapor present in the atmosphere depends on above which surface it is actually we are actually looking at. So suppose if we are looking at tropics, which is generally hot and humid, the amount of water vapor will be high. And if we are looking at dry regions, then the amount of water vapor will be less. So dry regions it can go it can be less up to 0%, and over tropics, over humid regions it can go up to 4 or 5%. So that's why we are telling 0 to 5%. And then there is carbon dioxide. The amount is so much less. That's why after that it is expressed in parts per million. So it is um, easy to represent because if we express in percentage, the value will be so much less. So then it is expressed in parts per millimeter, parts per million. Then carbon dioxide is around 380 ppm. Other are noble gases are counted. So that is the composition of that. Okay. So this is again, we discussed this in the last class. This is basically the vertical variation of temperature, vertical thermal structure of the atmosphere. So in this figure, basically the atmosphere is divided into different layers based on the temperature variation of the atmosphere. So we have four different layers, which is troposphere, stratosphere, mesosphere, and thermosphere. The lowest layer is the troposphere, and it is basically characterized by decreasing temperature with respect to height, and the lapse rate is generally told to be minus 6.5 degrees Celsius per kilometer, which means as we travel 1 kilometer in the atmosphere, there will be a decrease of 6.5 degrees Celsius to the temperature. Surface if it is 20, after going 1 kilometer up in the atmosphere, it will be 20 minus 6.5. That's what this basically tells. That is the lapse rate. So the lapse rate of troposphere is minus 6.5 degrees Celsius per kilometer. And this value, lapse rate value, fluctuates during day and night. It will be having a different value during day, and it will be different during night. And it also varies between season to season. So it basically depends on the amount of solar energy that is being received at the Earth's surface. So day and night it is different, and during seasons also the amount of solar radiation is varying. That's why the lapse rate in the troposphere is showing such a variation. And again, uh, the boundary of the troposphere is known as the tropopause. So as you can see, in the troposphere actually the temperature is decreasing. So the y-axis is basically altitude and x-axis is temperature. So we can see from surface to here the temperature is decreasing. Then we have tropopause, which is the boundary of the troposphere. In the tropopause actually the change of temperature with respect to height is 0. That is dt by dz is equal to 0 at all the boundaries. Like tropopause, the boundary of the troposphere. Then stratopause we have. There also it is not changing. Temperature is not changing with respect to height. Mesopause also it is not changing. So over all these boundaries like tropopause, stratopause, mesopause, the rate of the change of temperature with respect to height is 0. dt by dz is 0. That is troposphere. So yeah, again the tropopause height also varies uh, based on season. So if the temperature of the surface is high, the height of tropopause will be a bit higher. And when it is having a lower temperature, the height of tropopause will be a bit lower. So it is generally said to have a height of, so generally or on an average, it is having a height of 11 kilometer. But in the equator, which is comparatively at a higher temperature, the height of tropopause is 16 kilometer, whereas over poles, which is at a lower temperature, the height of the tropopause is around 8 kilometer. So that's how it varies. And the troposphere, this part of the atmosphere is generally being cleansed due to rain, cloud droplets, and all those things, because all weather activities happen over this region, like cloud formation, rainfall, ice, hail, all these things happen in this region only. So the atmosphere over this region is constantly being cleansed by these weather activities. So by cleansing, I meant the removal of aerosols. So I last class we discussed about aerosols. So aerosols are basically tiny solid or liquid particles that are suspended in the atmosphere. So these aerosols are generally are removed from the atmosphere by gravitational settling. That is, if the weight of these particles or mass of these particles are high, because of the gravitational force of the earth, it will settle down, which is basically known as dry deposition. And these are also removed through rainfall. When it rains, then also it is removed. So that is basically called wet deposition. The aerosols are acts as cloud condensation nuclei also. That is, it provides the surface for the water vapor to condense into. So that is another important characteristic of aerosols. So what I was telling us, like in the troposphere, the aerosols or these particles are being cleansed regularly by the weather activities. And then the next layer is the stratosphere. In the stratosphere, As we can see, the temperature is increasing with respect to height. So this pattern or this is called basically temperature inversion. The increase of temperature with respect to height. This pattern is called temperature inversion. And because of this pattern, the stratosphere is basically a stable or stratified layer. That is, it is not turbulent like troposphere. Troposphere is very much turbulent. Constant mixing is happening always, but stratosphere is stratified layer. Each layer is stratified. It is not mixing with each other. There is no vertical mixing or turbulence in this layer. So this is the layer in which ozone is present. So this increase with respect to height is basically caused by the ozone particles. The highest concentration of ozone is present at around 25 kilometer height. Okay, and the troposphere is basically, it extends up to a height of 50 kilometers. So that is stratosphere. And the third uh, layer is basically the mesosphere. So again in the mesosphere there is a decrease of temperature with respect to height, and then the boundary is called mesopause. The mesopause is the region with the lowest temperature in the atmosphere, which is around minus 80 degrees Celsius or 180 Kelvin. That is the temperature of the mesosphere. This is the coldest region in the Earth's atmosphere. That is mesopause, and above the mesosphere we have thermosphere. In thermosphere, temperature increases with respect to height. Um, this is basically due to the absorption of solar radiation, dissociation of particle, ionization, and all these things that we will discuss later. So that is thermosphere. So we have troposphere, stratosphere, mesosphere, and four different layers of Earth. The classification is based on temperature. So now let's calculate the lapse rate of the troposphere. I told you lapse rate is basically dT by lapse rate is basically dT by dz. Change in temperature with respect to height. So for that dT, we need T at surface and T at tropopause, right? So we are going to calculate the lapse rate of troposphere, that is dT by dz. So we need the T surface. What is temperature at the surface? From the graph, can you tell me? What is the temperature of the surface? Temperature at the surface? Anyone? Yeah. Yeah, 280 to 290. So let's take it around 288 Kelvin. Let it be 288. And then what is the temperature of the tropopause? At the boundary, what is the temperature? Yeah, 215, 219, 218, kind of like that, just close to 220. Let's take it as 218 Kelvin. So temperature at the surface, and we have temperature at the tropopause. Now we want to find Z. What is Z? Height of the tropopause. Height of the tropopause is coming as 11 kilometer. As you can see here in the y-axis, this is the height. So it is 11 kilometers. So we took T surface, then we calculated T tropopause. Now we have height. So now we can calculate dt by dz, right? So we want to calculate the lapse rate. Lapse rate is basically dt by dz, rate of decrease of temperature with respect to height. It is T surface minus T tropopause by Z. So from the graph, T surface has 288 Kelvin, and tropopause has 218 Kelvin divided by Z. Z we got as 11 kilometers. So what it will be? What will be the value? Yeah, it will come around 6.36 Kelvin per kilometer. So, okay, this is like dz will be 0. Surface we can represent as 0 minus z, minus sign. So, minus sign also will come here. 6.3. Basically, T2 minus T1 by Z2 minus Z1. Yes, T2 is 218 minus 280. T2 is like second letter by Z. So it will be minus 6.36 Kelvin. So this is the lapse rate of the tropopause. So the minus sign denotes that it is decreasing with respect to height. As we are going up in the atmosphere, the temperature is actually decreasing. So we calculated dT by dz, which is basically known as the lapse rate of the troposphere. I hope you got it. So we were talking about temperature variation, like till now, right? Now in the atmosphere, there is a pressure for the atmosphere, and the atmosphere is also having a density. So now let's look at how the pressure and density is varying. So in case of pressure and density, both of these quantities are having a nearly exponential decrease with respect to height. That is, the pressure and density are varying exponentially with respect to height. So suppose the surface pressure is P0. So both density and pressure vary exponentially. So P0 is the surface pressure, and P is the pressure at a height Z. Then P is given by P is equal to P0 e raised to minus Z by H. Okay, and this H is known as the scale height of the atmosphere, which is basically the height at which P becomes P0 by E, or the surface pressure reduces to 1 by E times. Pressure reduces to 1 by E times of its initial value. That height is basically known as the scale height. So P is equal to P0 into E raised to minus Z by H, where H is the scale height. So scale height is the height at which P becomes P0 by E. That is when Z is equal to H, then that equation becomes P is equal to P0 by E. So P is equal to P0 e raised to minus Z by H is the equation for the variation of pressure with respect to height. Z is the height at which the pressure is P. P0 is the surface pressure, and H is known as the scale height, which is basically the height at which the pressure reduces to 1 by E times its initial value or its surface value. And it is generally in the atmosphere, the value is around 7 to 8 kilometers. So that is pressure variation. Now in the same equation, if we take the log, log P by P0 becomes minus Z by H in terms of logarithm. Okay. So density is also having a similar kind of variation with respect to height. So if we look at the air molecules, as we can see, most of the air molecules are present very closer to the atmosphere. As we go up, it becomes very rare. Like it becomes rarer and rarer. Almost whole, like most of the molecules are concentrated in the surface of it. So now let's do one thing. So now we know how the pressure is varying with respect to height in the atmosphere. So let's find, as I said, the atmosphere is becoming rarer and rarer as we go up in the atmosphere. So let's find out, suppose the mass of the atmosphere, at what height the mass of the atmosphere is becoming half. Like if we take at one pressure, half of the atmosphere is above that pressure level and half is below. So m by 2 mass, when at what height we are getting. So we are going to basically calculate that. So at approximately what height above sea level does half the mass of the atmosphere lie above and other half lie below. So that's what we are going to calculate. So we have the equation P is equal to P0 e raised to minus Z by H. In terms of log, we have log P by P0 is equal to minus Z by H. So we want to calculate, what is the value we want to calculate? Z. We want to find the height of the atmosphere. And what is the condition that is given? At set height, mass of the atmosphere will be m by 2. Okay. So what is basically pressure? Pressure is basically force by area, right? And in case of atmosphere, if we are talking about atmosphere, what is the pressure that is being being exerted by the atmosphere on the earth, or exerted by the atmosphere on a particular level? So it is basically weight of the atmosphere at any layer. So if we consider, suppose this is the surface of the earth, we have the atmosphere here, and this is the surface pressure we are doing. So this is the weight exerted by the atmospheric layer on the surface. So the force exerted by the layer will be mg, right? Per unit area is pressure. So if you are considering the unit area, pressure will be basically mg, weight of the atmospheric layer above it. If we are looking at this layer, suppose if we want to calculate the pressure at this level, it will be the weight exerted by atmosphere above it, above that layer, right? So yeah. So what is the condition? At z height, the weight will be, or the mass will be m by 2. So the force will be basically mg by 2 into a. So mg by a, if m is the total mass of the atmosphere, mg by a is the pressure at the surface, right? Surface of the earth, if we are considering the surface, then mg by a is the pressure at the surface, which is given by P0, surface pressure P0 by 2. So P will be P0 by 2. Okay, I hope you got it. So the only condition that we have given is mass of the atmosphere will be half at height set. We want to calculate the pressure at height set, where m becomes, mass of the atmosphere is m by 2, which is basically P0 by 2. So P will be P0 by 2. That is the condition that we are given. So P is equal to P0 by 2. So we substitute it in our equation. That is log P by P0 is equal to minus Z by H. We will get it as log of P by P0 by 2 by P0, that is log of 0.5 will be minus Z by H. So assume H, as I said, is the scale height of the atmosphere. Assume the value of H to be 8 km. H is 8 kilometers. Then can you tell the value of Z? At what height the mass of the atmosphere will be half? What is the value of log 0.5? How much you got? Log 0.5 is 0.69. So Z will be minus 0.698 into H. Did you get? The value of Z will be? Yeah, it will come around 5.2, 5.5. Yes, so 5.5. Yeah, the value will come around 5.2, 5.5. So what that basically tells us that when we travel around 5 kilometer of the around up to 5 kilometer of the atmosphere, almost half of the atmosphere is over. Like almost half of the mass of the atmosphere is present below 5 kilometer. Like 50% of the atmosphere is below 5 kilometer. 5 kilometer means we haven't even reached the top of the tropopause. It is just half of the troposphere. So almost 50% of the mass of the atmosphere is present. Just half a like at half of the troposphere, almost 50% of the atmosphere is present. So when we reach around 32 kilometer, almost 99% of the mass of the atmosphere will be below. So only up to 32 kilometer actually most of the atmosphere exists below 30 kilometer, 30 to 32 kilometer. So that's what we got from here. So since the variation is exponential, like as both density and pressure is varying exponentially, almost uh, whole part of the atmosphere is present in the lower layers of the atmosphere. So just now we calculated like almost 50% of the atmosphere is present within 5 kilometers, like half of the troposphere. So that is pressure and density. Okay. So both is having an exponential decrease. P is equal to P0 e raised to minus Z by H, where H is known as the scale height of the atmosphere, which is basically the height at which the surface pressure becomes 1 by E, or like the pressure becomes 1 by E times the surface pressure. Then P becomes P0 by E. That height is known as the scale height, and that height is generally 7 to 8 kilometer in the atmosphere. Then we calculated at what height half of the atmosphere will be present. So for that we did so we have we have the equation and we have to calculate Z, and what we have is mass of the atmosphere, which is basically m by 2. So from P is equal to F by A, we found that P will be at a height Z, the pressure will be P0 by 2. So using that equation, we just calculated the height. So it is coming as 5 kilometers. So yeah, that's it about pressure. Now let's have, now people are joining. Okay. So let's have a look at, so we learned to classify the atmosphere into different layers based on temperature. So based on temperature, we classified it into troposphere, stratosphere, mesosphere and thermosphere. Then Another type of classification is we can classify it based on the composition of the atmosphere. So based on the composition of the atmosphere, it can be classified into two: this homosphere and heterosphere. So you can see this is homosphere, and above this is heterosphere. Like from the top of the thermosphere, it is heterosphere, till thermosphere, it is homosphere. So this classification is basically based on the composition of the atmosphere. So in the lower layers, that is in the homosphere, basically the composition of the atmosphere is almost same. Like that is the 78% nitrogen, 21% oxygen. This composition remains same throughout the homosphere till the thermosphere. What happens after the thermosphere is that the energetic rays from the sun starts to um, okay. Okay, in the heterosphere, what happens is that because the atmosphere is very rare over there, like as I was saying, said many the number of molecules that is present in the heterosphere is very less. It is becoming very rare actually. So as we can see here, as we go up, the number of molecules present in the atmosphere is very less. So as we reach up to the thermosphere, there will be very less amount of molecules present over this region. So what happens is that the collisions between the molecules will be, there won't be much collision between the molecules, and it will be almost like kind of static in the heterosphere. So what happens is that the heavier molecule starts to settle down and lighter molecule starts to go up in the atmosphere. So it is kind of heavier molecules such as oxygen and atmosphere will be settled in the top, bottom of the heterosphere, and lighter molecules will be in the will be floating above the base of the thermosphere, or at the top of the atmosphere. And lighter molecules will be at the top of the atmosphere, and heavier molecules will be at the bottom of the thermosphere. So this is known as the heterosphere. So in homosphere, because there is mixing and the molecules are very high, that concentration of 78% nitrogen and 21% oxygen remains same throughout the homosphere. But after, like in the thermosphere basically, and above the homosphere, the because the number of molecules is very less, the molecules are not turbulent. So what happens is that because it is kind of static, the lighter molecules, the heavier molecules start to settle down, and lighter molecules uh, float in the atmosphere. So that is the heterosphere. So this is a classification based on the this is a classification based on the composition of the atmosphere. Now let's look at the classification based on electrical properties of the atmosphere. So there is a layer or a region in the atmosphere which is basically known as the ionosphere. So ionosphere is actually in the upper atmosphere, or above 60 kilometer. From 60 kilometer, this region starts in the atmosphere. So 60 kilometer means it will be there. So 60 kilometer means it will be like half of mesosphere, like mostly thermosphere. From 60 it begins. Ionosphere begins from 60 kilometer and it extends to a higher height, to 120, 200 kilometer like that. So this an electrified region in the atmosphere is basically known as the ionosphere. So why it is called as ionosphere is because in this region, this is basically the top layer of the atmosphere, right? We have reached almost the top. So it is basically half, it starts from half of mesosphere. So what happens is that high energy X-rays and ultraviolet light from the sun are constantly colliding with the gas molecules present in this layer. So in this layer, the gas molecules are constantly being collided by the high energy X-rays and solar rays that are coming from the sun. So as a result of these collisions, um, what happens is that the electrons from these molecules or atoms are knocked out, and as the electrons are removed or knocked out from the atoms and molecules, these atoms or molecules turn into charged particles, which is known as ions. So because of the formation of ions, the sphere is basically called ionosphere. So this region of the atmosphere basically contains charged ions and free electrons. So the atoms or molecules are being collided by solar rays, high energy solar rays and X-rays. So the electrons are being knocked out from these atoms and molecules, and these atoms and molecules turns into ions and then free electrons. So the lower region of the ionosphere, that is from 60 kilometer, it extends up to around top of the, it starts at 60 kilometer and extends up to around at the towards the top of the atmosphere. So there are basically three regions within the ionosphere. So the D region, which is the lowest region, is starting from about 60 or 70 kilometer. It starts from 60 or 70 kilometer and extends up to 90 kilometer of height. And then the next layer is known as the E layer. So the E layer starts from 90 or 100 kilometer and extends up to 120 or 150 kilometer. That is the E layer. And then above the E layer, we have another layer, which is the F layer. So F layer starts from 150 kilometer and is up to as high as 500 kilometer, like almost the top. It is considered as the top of the atmosphere. So 180 kilometer to around 500 kilometer, this region exists. So there is three subregions, D, E, and F layer. And actually, the existence of these three different layers and the height of the ionosphere basically depends on the, and it basically varies based on the time. So as I told, the ionosphere is basically formed when high energy solar rays or X-rays collides with the atoms or molecules and knock out the electrons from these atoms or molecules. So only during daytime the solar rays are present. During night solar rays are not coming. So once these ions and electrons are found, there are chances that it will recombine with the free. Some ions may recombine with the electrons and then go back to neutral atoms or molecules. So during daytime, the amount of ions that are produced are far higher than the amount of atoms or molecules that are being that are combining back, like that are being going back to atoms or molecules by the combination of free electrons and ions. So the production of ions are greater than their recombination. So that's why during daytime we can distinctly see these three layers in the ionosphere is D, E, and F layer. Whereas at the night time, because there is no incoming solar rays or X-rays to produce these ions, the combination, the recombining of ions and electrons are more, which leads to the like almost disappearing of D region and the weakening of E region, and only F region will be present during night time. So that is happening during night, and during daytime all three layers are present. And this region is basically told to be very much helpful for radio communication. So during daytime, actually, the AM radio waves that are being emitted from the from the surface of the earth is being absorbed by the D layer, is being reflected back. Some part is being reflected back and some part is being absorbed by the D layer. So the signal is basically lost during daytime, and whereas during nighttime, because the disappearing of D layer, it reaches up to the F layer, which reflects back this layer, and by this multiple reflection from the F layer and the surface, these radio waves are able to travel far distances, whereas during daytime the signal is actually lost. So this is because of this reflection of the F layer, it is we are able, because this radio waves are actually able to travel longer distances. So it is considered to be very much important for radio communication. So yeah, that is ionosphere, the highest, the ionized layer or which has electrical properties in the atmosphere. Okay, so yeah, that's all about ionosphere. Okay, now let's have a look at. So this is an entirely different setting. Regarding atmosphere, we have discussed almost all of. We have covered almost all topics. Like we have talked about the composition of atmosphere, which is mostly composed of nitrogen and oxygen. And please remember these numbers like 78%, 98 oxygen. That numbers are important. and argon is the third abundant component in the atmosphere, and water vapor is having a varying composite, like it is varying, and that the amount is varying in the atmosphere. And then we talked about the thermal structure of the atmosphere based on the temperature. Layers are divided into four different layers. And then we calculated lapse rate of the troposphere. Then we uh, studied that how this pressure and density is varying in the atmosphere, which is having an exponential decrease, both pressure and density. And then we found that almost half of the atmosphere is present within 5 kilometers of the atmosphere. So it is getting the air molecules are becoming very much less as we go up in the atmosphere. Most of the atmosphere is present in the lower layers only, up to the troposphere or up to half of the stratosphere only. Almost all of the air molecules are present. As we go up after that, it is very much the number of molecules that we can find will be very much less. So that's what we found. And then we found the classification based on composition, which is homosphere and heterosphere. Then we learned about the electrical properties of the atmosphere, which is basically ionosphere, and different layers in the atmosphere, how it changes during day and night time. So this much we learned about atmosphere. Now let's have a look at another topic, but it is an entirely different topic actually. So let's see. There are if we when we talk about the weather activities or weather phenomena that are happening in the earth, we can classify it into different types or different scales based on the region uh, which is being affected by this weather activity, and also based on how much time this phenomenon is actually persisting. Okay, so if you look at this figure, the x-axis is basically distance, which is given in meters, and the y-axis is actually time, which is given in seconds. Okay, and we have different types of scales. So when we talk about the scales, we have four different scales in the atmosphere, which is basically different scales in the atmosphere, which is basically micro, meso, synoptic. One more is there, which is known as planetary scale or global scale. So this basically depend upon the area up to which this region, like how much region is being affected by this weather phenomena, and for how much time this phenomenon is persisting. So if we start from this region basically is the planetary scale phenomenon. So this is actually, if we look at this, persisting from months to years, several months to several years. This phenomenon it is having a 10 raised to 6 to 10 raised to 7 meters. This 100 to some 100 or 1000, several thousands of kilometers. This is having the effect. So that is basically the planetary scale phenomenon. And the climate variation that we are talking about, it is actually a global phenomenon or planetary scale phenomenon, because this climate change is not only affected, uh, is not only applicable to a small area. Like this climate change occurs everywhere, not only in India, not in US, not in Africa. It is a global phenomenon. It is happening over the whole globe. So climate change or climate variation is one example of this planetary scale phenomenon, and it is existing over like hundreds of years. This thing is existing, or it will persist for a longer time. And the scale is also, it is affecting the whole globe. So climate variation is one example. And another phenomenon is known as ENSO. I don't know if you guys have heard about this. So this is basically a oscillation in the atmosphere. It's basically known as El Nino Southern Oscillation. So to put it simply, you would have heard about El Nino, La Nina, all papers and all. Whenever we talk about monsoon, you would have seen newspaper clips and all telling like the rainfall will be less because this is a El Nino year. And when we are talking about temperature also, you would have seen, since it is an El Nino year, the temperatures are supposed to be high, and this year it is a La Nina. So maybe you would have seen all these things. So basically, ENSO is actually a warming that is occurring over the Pacific Ocean. Okay, this happens over the Pacific Ocean, but it is affected. So this is India. We have Indian Ocean here. So this is being affected here also. If some convective activity or something is happening here, because of the atmospheric circulation, this will have an impact over other oceans also. It is not, whatever is happening over this region is not only concentrated or is not only affecting the nearby regions, but it is being transmitted or it is being affected to regions which are far away from that also. So ENSO or El Nino is basically a phenomenon that is occurring in the Pacific Ocean, but it is having an impact whole over the globe. So even for Indian monsoon, generally we look for what is the phase of ENSO. Is it positive, is it negative, and all this. So again, this is another example of planetary scale phenomenon, because as I said, it is having an impact over the whole globe. So the scale is high and it persists for several months. So that is another example. Then yeah, then in atmosphere we have different waves also, like atmospheric waves. Like we have oceans, we have waves. Like in ocean we can actually picturize it. In atmosphere also we have kind of waves, which is basically convective and um, like rising and sinking branches of clouds and all those things. So that is also another example of planetary or global scale phenomena. So then if we go to the next, just below the planetary scale, we have the synoptic scale phenomenon. So synoptic scale phenomenon, it is around 10 raised to 5 to 10 raised to 6. It comes in this um, length scale, maybe 10 raised to 5 to 10 raised to 6 meter, whereas in the time scale it is day to week or day to month. So synoptic scale phenomena persist from several days to several weeks. So the example of synoptic scale systems are tropical cyclones. This thing most of you guys will be familiar with. Cyclones are like, most of us are hearing about cyclones and all those things. So tropical cyclones is a synoptic scale phenomenon. So then we tell it is a phenomenon that is happening at a synoptic scale. So you know, like when we are talking about cyclone, if there is a cyclone in the Arabian Sea, it will be uh, if suppose a cyclone, there is a cyclone in the Arabian Sea, it will affect the Indian region, right? If a cyclone is there, it will affect this region. So it is not globally, it is not affecting, but it will affect the nearby regions. Like in Arabian Sea, if there is a cyclone, it will affect India, and here some part of China and all. It will some changes in rainfall and all will be there. So this is not affecting globally, but it is affecting the nearby regions. Um, where it is occurring. So that's why it is just below to what we call global scale or planetary scale. So that is synoptic scale phenomena, and we know cyclone persist for several days to, like from low pressure if we are considering, as it grows maybe it persists one or 2 weeks or something. So basically weeks to month these phenomena persist, and cyclone is an example. Cyclone is basically a synoptic scale phenomenon. Another example is friends actually. Friends is basically mid latitudes and all. These are the weather. These are the what do you say? These are which are the reason for the weather activities over there. So friends, just imagine there is one cold air mass and there is one warm air mass. The region where it meets is basically known as the front. So where the region where it meets will have several weather activities like rainfall, thunder, and all those things. So these are basically known as fronts. So this is also a synoptic scale phenomenon. Now going one step again below, mesoscale phenomenon. So mesoscale is basically um, in a time scale of 10 raised to 3 to 10 raised to 4. 10 raised to 2 to 10 raised to 4 it will come, that much meters, and it persists for several hours to a day. That is a time scale up to which it persists, hour to day. So an example of this is thunderstorms. Thunderstorms, we know, like very heavy clouds. It will cause rain. It will cause rain over a smaller region, right? Suppose if we have a thunderstorm or mm, what is it, the extent is comparatively less. Like if we have, suppose in Bhubaneswar there is a thunderstorm, it will rain maybe over Bhubaneswar, not like entire Odisha or anything. So like the scale up to which this will have an effect is less compared to synoptic scale. So that is thunderstorm. And then tornadoes are also an tornadoes maybe you would have seen in movies and all. So this is basically forming in land actually. It is also kind of um, like moving circulation kind of thing. This is also a mesoscale phenomenon. It will have a the impact, the region where it will have an impact will be less compared to synoptic scales. These are two examples of mesoscale phenomena. Now we have microscale phenomena. Microscale phenomena, turbulence and all comes under microscale phenomena. Small turbulence from the surface and all these things comes under microscale. We have four different scales: planetary or global scale, synoptic scale, mesoscale, and microscale. Planetary or global scales means the it will persist for several months to several years, and the length scale will be basically greater than 10,000 kilometer or something like that. Yeah, planetary scale it will be greater than 10,000 kilometer, and it will have a time scale of several months to several years. So the global warming is a planetary scale phenomenon. It is affecting the whole globe. Then we have atmospheric waves such as Rossby waves and all. Maybe you will study this in the coming chapters. So this is just an atmospheric wave. Just imagine just like we have waves in the ocean, we have atmospheric waves also. We cannot see it basically, but it has a large impact on the weather systems as the waves are moving. So that is another example of planetary scale phenomena. Then global wind systems. Global wind system also we have. This one maybe I'll explain to you what is this later. I think you will study this also. What are the global wind system? We have different cells in the earth, in the surface, mid latitudes, then in poles. We have different wind circulation. That is also global phenomena. Then we have synoptic scale phenomena. Synoptic scale phenomena essentially exist from several weeks to months, kind of. So cyclones are an example. Then we cyclones, friends, and all are an example of synoptic scale phenomena. 500 to 10,000 kilometer is a region which it have an impact. Then we have mesoscale. Mesoscale exists from several hours to several days, maybe. So it is having an impact of 2 to 2,000 kilometers. That much region it will have an impact. Thunderstorms, tornadoes, all these things are an example of mesoscale phenomena. And then we have microscale phenomena, like small eddies, small plumes, then cumulus clouds. All these are examples of microscale phenomena. And below that we have molecular scale, which is having an impact of less than 2 millimeter. Very small impact it has. That is molecular scale. So yeah, these are the different scales of atmospheric motion. When we talk about a weather phenomenon, we generally look into at what scale it is happening. So to understand how long the system will persist, and also to know how much region will be affected because of this phenomenon. The classification will help us to identify the impact or the effect of the weather system that we are discussing. That's why this classification has come. So four different classifications. I hope it is clear. So yeah, that's what I thought to discuss today. If you guys have any doubt, you can ask. Any doubts, problems that we did, you guys have any confusion or anything? I hope you were able to solve the questions. Okay. Or you want me to explain any section once more or anything? Or else if everything is fine, let's end today's session. Thank you. But if you have any doubt, you can always ask. But I think that discussion forum is also there. If you don't want to ask, you can always post the question there also. Okay. If nothing else, then yeah. Oh, then thank you. Okay, then let's stop. Yeah. Thank you all. Bye. Good night.